Hello, my name is D. Charnavit from SRIT College. Today I am going to present a video presentation on molecular orbital theory, understanding chemical bonding at the quantum level. Coming to why MOT matters. Coming to the beyond classical models, MOT explains molecular bonding in ways that classical models such as Levy structures and valence bond theory cannot fully capture. Coming to the foundation for modern chemistry, it serves as a fundamental pillar for modern computational chemistry, spectroscopy, and material science. At last, resolving mysteries, the theory provides elegant explanations for phenomena like the paramagnetism of O2, which older theories failed to account for. The quantum leap from atomic to molecular orbitals. Formation of molecular orbitals. In MO theory, atomic orbitals combine to form new molecular orbitals that span the entire molecule rather than being localized to individual atoms. Electron delocalization. This process means electrons are delocalized, shared across multiple atoms. This provides a more accurate representation of electron distribution and chemical bonding. The groundbreaking concept was pioneered by scientists like Hunt, Mulliken, and Leonard Jones in the early 20th. Coming to the bonding versus anti-bonding molecular orbitals. Bonding orbitals formed by constructive interference of atomic orbitals. Electron density is concentrated between the nuclei, stabilizing the molecule by attracting both nuclei towards this region. Anti-bonding orbitals result from destructive interference. Electron density is concentrated away from the nuclei, leading to a node between them, which destabilizes the molecule. Consider the simplest example, the overlapping 1s orbitals in H2, which forms a sigma bonding orbital and sigma star anti-bonding orbital. Sigma and pi orbitals. Sigma orbitals. Electron density is concentrated along the internuclear axis, formed by direct head-on overlap of atomic orbitals. Examples include the H2 molecule or single bonds in molecules like ethane. Pi orbitals. Electron density is located above and below the internuclear axis, formed by the sideways overlap of p orbitals. Examples include double and triple bonds such as in O2 or ethylene. Both sigma and pi orbitals exist in bonding sigma comma pi and antibonding sigma star comma pi star forms, each with distinct energy levels and electron distributions. Constructing molecular orbital diagrams, the case of B2 and O2, boron dimer B2. Valence electrons, B2 has 10 valence electrons. Electron filling, electron fills MOs according to Hund's rule and the Pauli exclusion principle. Paramagnetism, the diagram shows two unpaired electrons in the pi bonding orbitals, which explain B2 is paramagnetic behavior. Bond order. The calculated bond order is 1, indicating a single bond. Oxygen molecule. It has 12 valence electrons. The MO diagram shows two unpaired electrons in the pi antibonding orbitals, providing a quantum explanation for its observed paramagnetism, unlike valence bond theory. A bond order of 2 is calculated, aligning with its double bond character. Calculating bond order and predicting stability. Bond order is equals to number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding molecular orbitals divided by 2. Predicting existence or stability. A positive bond order indicates a stable molecule that can exist, meaning there are more electrons in bonding orbitals than in anti-bonding ones. A bond order of 0 or negative implies that the molecule is unstable or will not form under normal conditions. Example, He2 would have a bond order of 0. Practical applications. This calculation is a crucial tool for predicting molecular existence, relative bond strengths, and even properties like bond length. Molecular orbital theory in action, explaining spectroscopy and magnetism. Spectroscopy insights. The slide explains that the interaction of light with matter provides an experimental window into molecular energy levels. This interaction helps in validating and refining the concepts of molecular orbital theory. Magnetic properties. Molecular orbital theory effectively explains the magnetic properties of molecules. The presence of unpaired electrons in a molecule results in paramagnetism, a property that simpler models often cannot accurately predict. Historical impact on modern applications. Pioneering minds. This section features illustrations of three historical figures likely significant chemists or scientists, and briefly mentions their contributions to chemical understanding, possibly related to bonding or computational chemistry. Computational chemistry and cutting edge application. This part discusses modern applications, possibly detailing how complex computations are used to create or understand various chemical structures or processes. An abstract starburst like graphic is present in this section. Molecular orbital theory, the quantum key to chemical bonding, paradigm shift. MOT transformed the perception of molecules from static, localized bonds to dynamic, delocalized electron clouds. Electrons in a molecule move through the entire molecule rather than being confined to individual atoms. Precision prediction. The theory empowers chemists to predict molecular properties and behaviors with unprecedented accuracy and detail, including stability, magnetic properties, and electronic transitions. Dynamic systems. MOT invites a view of molecules as intricate quantum systems that are constantly interacting and evolving. It explains how atomic orbitals combine to form molecular orbitals, which determine the probability and density of electrons. Thank you for sharing your valuable time with me.